Hi, I'm Antti, and I'm presenting our paper Low-Step Multi-Commodity Flow Emulators, joint work with Bernard, Ellis, Jason, and Touchable. So the multi-commodity flow problem is a very classical problem. We consider the problem, both the concurrent and non-concurrent variants of the problem, in undirected graphs with capacities. In the multi-commodity flow problem, you are also given a demand which essentially describes how you should send flow. Then for output, you want to output a single commodity flow between each pair of vertices in the demand. The sum of these flows should be capacity respecting. What this means is that the amount of flow in total you send over any edge should be at most the capacity U of the edge. Then, depending on the variant, in the concurrent variant, you have to send a multiple of the demand. That is, the flow between A and B has to be lambda times the demand of A and B for the same lambda for all A and B. Then in the non-concurrent variant, you can send however much flow you want between the vertex pairs, except you cannot exceed the demand between A and B. So you can send zero flow even if there's demand, but you cannot send more. And also in the non-concurrent case, it's often assumed that the demand is either 0 or infinity. Regardless of the variant, you want to maximize the total amount of flow you are sending. So what algorithms are there for multi-commodity flow? Madry in 2010 gave a M times N time algorithm for both variants. Then, when the number of commodities k, that is the support size of the demand, is small, these two results gave better dependence on M and N for non-concurrent and concurrent flows. However, in the case where N, M, and K are all around equal, all of these algorithms are at least quadratic time. Trying to go below quadratic time, however, we hit the flow decomposition barrier. So if you recall, the output of multi-commodity flow is k single commodity flows. And each single commodity flow could in principle have flow on all M edges of the graph, which would mean your output size is M times k. Are there graphs where M times k is necessary? Yes, even this very simple graph requires any competitive output in both the concurrent and non-concurrent flow variants to have size omega M times k. So what can you then potentially do? Well, if you assume both unit capacity and non-concurrent, this counterexample doesn't work. Otherwise, the output size can be large, and you can't get around that unless you only output the value of the optimum flow instead of the optimum flow itself. So, what faster algorithms than quadratic are there for multi-commodity flow? Well, if you use a hierarchical cut structure, you can reduce the problem to one on a tree. And on a tree, both concurrent and non-concurrent flow are easy to solve. However, this costs you a polylog factor in approximation, since the cut structure doesn't perfectly approximate the cuts in the graph. And of course, this only gets you the value of the flow. Then a recent line of work in the unit capacity non-concurrent case achieved polylog-log approximation. We achieve constant approximation in the same near-linear time for both concurrent and non-concurrent flow. Additionally, while explicit flow is impossible because it could be that any competitive flow needs to be large, we give an implicit representation of the output flow. So what does it mean to give an implicit representation? Well, let's look at this counterexample graph again. If you just replace this long path here with a single edge, then suddenly there exists a very small flow. Then we can also store for this edge we added that it corresponds to this long path in the original graph. In general, the implicit representation consists of the vertices of the original graph stacked in a bunch of layers. Then, at each layer, we have some added edges, and each edge corresponds to some path at the previous layer. And again, an edge at every layer, it corresponds to a path at the previous layer, but it also implicitly defines a path at the bottom level by just concatenating the implicit paths of the edges that appear on its path at the previous level. And also, the topmost level defines the flow, where each edge here corresponds to a flow path at the bottom level, and we also store with the edge the flow value of the corresponding path. Now, with this structure, we can compute things about the flow, implicitly represented flow, such as the value of the flow by just summing up the capacities at the top level, the congestion of the flow on every edge by just going top down and computing at every level the congestion of every edge. We can also compute the congestions for a given subset of commodities and such. And also we can answer queries such as, what is the ith edge of the jth flow path between A and B? Again, just by going top down. So again, our result is a near linear time algorithm that finds an implicit representation of a constant competitive flow. And this works for both concurrent and non-concurrent flow. Before our work, even the existence of sub-quadratic size constant competitive implicit representations was open. Our algorithm also generalizes to mean cost multi-commodity flow, which in fact we must solve as a subproblem. And our algorithm works in parallel with depth and to epsilon. The key ingredient, low-step multi-commodity mean cost multi-commodity flow emulators that we use to achieve the result, we believe is also of independent interest. So in the rest of the talk, I'll go into the low-step mean cost multi-commodity emulators, the definition, the results we achieve with them. And of course, before that, I need to give some definition for the setting with lengths, as these are mean cost multi-commodity flow emulators. So we need to introduce costs, or in this case lengths, as we refer to them. Then after that, I'll give a very brief overview of the other pieces that we need to achieve the multi-commodity flow algorithm. So in the setting of with lengths, graphs in addition to capacities have lengths. So every edge has some strictly positive lengths. And flows now assign flow to paths in G rather than edges. The congestion of a flow is again just the congestion, maximum congestion of an edge, which is the sum of paths that cross the edge, flow on the path, divided by the capacity of the edge. The total length, or essentially cost of the flow, is the sum over the flow paths, flow on the path times the length of the path. And the step length of the flow is just the maximum number of edges on any flow path. So for example, a 3-step length flow must have at most 3 edges in any flow path. We say that the flow F routes demand if the sum over all paths from A and B, the flow on the path, is equal to the demand between A and B. So now, informally, low-step mean cost multi-commodity flow emulators are a graph simplification that preserves all mean cost multi-commodity flows. However, it also guarantees that there exists mean cost multi-commodity flow routing the same demand with very short step lengths. And again, this means that all flow paths have very few edges. This turns out to be extremely algorithmically useful. More formally, a T-step emulator, where T is the bound on the step length of flow paths, is a graph H on the same vertex set, along with a mapping from the edges of H to paths in the original graph. That guarantees the following 2 things. First, for every flow F star on the original graph, let D be the demanded routes. there exists a flow f prime routing the same demand on the emulator, such that the congestion is not much worse. It's kappa times the congestion of the original graph, where kappa is the congestion slack parameter of the emulator. Its total length is not much worse, which is length slack of the emulator times the total length. And this flow f prime has step length at most t. That is, any flow path in it contains at most t edges. Then in the other direction, for any flow on the emulator, if you project it down to the original graph using the mapping pi, the congestion of the flow does not get worse, and the total length of the flow does not get worse. So that means at the cost of a factor kappa in congestion and factor s in the total length, you can look for flows on the emulator and then project them down. However, what this achieves is that you can guarantee to your algorithms that there exists a competitive flow where the step length, that is the number of edges on any flow path, is small. What do we achieve? What kind of low step flow emulators do we achieve? And of course the parameters, congestion slack and length slack. What kind of flow emulators do we achieve? Constructively, for any epsilon, we achieve step bound, which is constant depending on epsilon, length slack, which is constant depending on epsilon, and congestion slack, which is n to epsilon. We can also compute such an emulator in time number of edges in the graph to 1 plus epsilon. And we can also do this with depth, number of edges in the graph to epsilon. The flow mapping, the mapping pi of edges in the graph to paths in the original graph is implicit then. So it has the same implicit structure as the implicit flow representations we have in the end. In fact, the implicit flow representations we output just consist of the emulator and an explicit flow on top of the emulator. We also give an existential result for emulators that is a tighter trade-off. So now we have seen the definition of emulators and our result for emulators constructively. And emulators, they reduce mean-cost multi-commodity flow problems into short mean-cost multi-commodity flow problems. However, we subline the congestion slack is n to epsilon, and we want constant approximation. And also, it's not at all trivial to solve short mean-cost multi-commodity flow problems approximately. The solutions we have to this is first, you can boost away the congestion slack. If you have a certain congestion slack, length slack, approximate mean-cost multi-commodity flow solution, you can boost it to approximately length slack, approximate mean-cost multi-commodity flow solution. And recall, the length slack is constant, which again depends on epsilon, but we can just select epsilon to be any arbitrary small constant. The boosting here is very similar to the boosting of Gaugen-Kahneman. Notably, the boosting is enabled by the implicit representations we use, because this boosting technique needs to know the congestion of every edge, and the implicit representation can map this down. Also, in the end, the boosting produces the final flow as a convex combination of the flows it had midway. So it is again just the implicit representation, because all of the flows you had produced were implicit representations. Then, to solve the short mean-cost multi-commodity flow problem on top of the emulator, we give a high-commodity short flow algorithm. What this high-commodity means here is that there's no runtime dependency on k. Or, well, the runtime dependency on k is additive instead of multiplicative. So even if you have n-ish commodities, it runs in time n to 1 plus epsilon. The way we achieve this algorithm is by really abusing the hammer of length constraint expander routing and length constraint expanded decompositions. All right. So in this talk, I don't have time to go into the details of the algorithm, but we actually have a length constraint expander workshop here at STOC. And at this workshop, we will cover how we actually achieve low-step emulators. And on the second day, on Wednesday, I'll also go into detail on how the constant approximate mean cost multi-commodity flow result is actually achieved by using emulators along with boosting and the new flow algorithm for short mean cost multi-commodity flow.